Determine whether the following relations R1, R2 and R3 are reflexive, symmetric or transitive. So here we have three relations R1, R2 and R3. So before coming to the problem, so what we'll do, we're going to quickly recap what it means when we say that a given relation is reflexive, symmetric or transitive. So let's start with the property of a relation being reflexive in nature. So here R is a relation, let's say, which is defined on some set A. So R, let's write it out. R is defined on some set A, such that R is going to be reflexive in nature. R is reflexive with a condition being if and only if A comma A, where A is an element belonging to the set A. Let's write it down. With A belonging to the set A, so A comma A belongs to the relation R. So when we have this ordered pair A comma A belonging to the relation R, then we can say that R is reflexive. Okay, next is, let's say we have two elements A and B belonging to that same set A. Then the ordered pair A comma B, if it belongs to the relation R, then it must imply that B comma A, that ordered pair, all we've done is interchange the position of the elements in the ordered pair. So here A comes in the position of B and B comes in the position of A. Then the ordered pair, new ordered pair that we get, B comma A, this must belong to the relation R as well. That in that case we say that the relation R is symmetric. This is a symmetric relation on the set A. And then finally what we'll do, we're going to consider three elements A, B and C, all belonging to the set A, such that if we have A comma B, the ordered pair A comma B belonging to the relation R, and we have another ordered pair B comma C belonging to the relation R. Now here the way we are choosing the ordered pair, that's very important. So as you can see here, the second element in the first ordered pair A comma B, they must match exactly with the first element of the second ordered pair. So in our case, both of these elements are B. So here, then it must imply that the ordered pair A comma C belongs to the relation R. Then if this becomes the case, then we can say that our relation R is transitive. So this is what we mean when we say that a given relation is transitive. So here we are provided with three relations, R1 and R2 and R3. We're going to check whether they are reflexive, symmetric or transitive using a definition. So let's start with our first one. So here we have a relation R1 on Q0. So here Q0 represents the set of all non-zero rational numbers, and it is defined as the ordered pair A comma B belonging to the relation R1 if and only if A equals to 1 over B. So that's the definition. Now using this we are going to check for its reflexivity, symmetricity and transitivity. Let's start with reflexive one. So reflexive, according to the definition, R1 is going to be reflexive if and only if A comma A belongs to R. So what does it mean when we say that A comma A belonging to R1? What does it imply? This must imply that A must be equals to 1 over A. So A must be equals to 1 over A. That's what it means, because the definition here A equals to 1 over B if we have the ordered pair A comma B belonging to R1. Now in our case B here is actually A. So what we have done here in this equation, A equals to 1 over B, we have replaced B with A. So that is giving us A equals to 1 over A. Now do you think this is a possibility? No, this is not a possibility. A cannot be equals to 1 over A. Because now let's say we have an example. Let's say we consider A to be equals to some rational number 2 over 3. That would mean that 2 comma 3 comma 2 comma 3, this ordered pair, this would mean if it belongs to, let's say we assume that this belongs to the relation R1, then according to this definition, this should mean that 2/3 must be equals to the reciprocal of 2/3, which is 3 over 2. But how can 2/3 be equals to 3 over 2? That's not possible. So this means that this ordered pair cannot belong to R1, so that does not belong to R1. So here we can say that our relation R1 cannot be reflexive. So this is not a reflexive relation on the set of non-zero rational numbers. Fine. Now coming to the second part, which is we have to check if it is symmetric or not. So to check for symmetric, so what we'll do, we're going to consider two elements A comma B. So let's say both of these two elements belong to the set of non-zero rational number. Then, according to the definition, if we say that A comma B belongs to the relation R1, and then this would imply that A is going to be equals to 1 over B. That's the definition. Now, A equals to 1 over B, we can also rewrite it as B equals to 1 over A. Now, writing B equals to 1 over A, this simply means that we have B comma A belonging to the relation R1. So just use the definition. So here A comma B belongs to R1 means A equals to 1 over B. And if you say that B comma A belongs to R1, that is simply replacing A with B and B with A, which is going to give us B equals to 1 over A, and that's what we got. So this is telling us that our relation R1 is actually symmetric in nature. This is a symmetric relation on the set of non-zero rational numbers. And then finally, we're going to check if it is transitive or not. So here, what we'll do, we're going to consider three elements, A, B, and C. So let's say these three elements, A, B, and C, belongs to the set of non-zero rational numbers. Now, A comma B belonging to the relation R1 and B comma C belonging to the same relation R1 must imply that we should get A comma C belonging to R1. That is what we need to check whether in order to say if it is transitive or not. Now let's say if it is true or not. Now what does it mean when you say A comma B belongs to R1? So by definition A is going to be equals to 1 over B. And if we say that B comma C, this ordered pair belongs to R1, this means that B must be equals to 1 over C. So all we've done is wherever we see A, we're replacing it with B, and wherever there is C, there is B, we're replacing it with C. That's why we're getting B equals to 1 over C. Now, let's try to equate these two equations. So here, what we'll do, so here B will be equals to 1 over A, and we're going to replace this B into this equation so that we get 1 over A equals to 1 over C. And that's giving us A equals to C. However, we are not getting the condition that A equals to, that means here we are saying that A cannot be equals to 1 over C because we're getting A equals to C. We actually needed A equals to 1 over C in order to say that A comma C belonging to R1. So this means that the ordered pair A comma C does not belong to the relation R1. So it's not belonging to R1. That means it fails the test for transitive. So here our relation R1 is not transitive. This is not a transitive relation on the set of non-zero rational numbers. So here we have shown that the relation R1, this is only symmetric. It is not reflexive and it is not transitive. Now let's go to the second one. Now we have another relation R2 which is defined on the set of integers, and it is defined by the ordered pair A comma B belonging to the relation R2 if and only if absolute value of A minus B is less than or equals to 5. Okay, now here let's do one thing. Let's rewrite the relation that will help us to understand the relation in a more easier fashion. So R2 is a relation which is going to contain the set of ordered pairs given by A comma B such that the absolute value of A minus B less than or equals to 5, and here both A and B must belong to the set of integers. Fine. Okay, now and here it's given there R2 is defined on the set of integers. That it simply means that R2 is a subset of the Cartesian product of the set of integers with itself. Fine. Okay, let's check for reflexivity. To check for reflexivity, here what we'll do, we're going to consider an element A which is an integer. So this is going to be an arbitrary element that we are choosing. Let A be an arbitrary element belonging to the set of integers Z such that we have A comma A. So if we take the ordered pair A comma A, what does it mean? A comma A belonging to the relation R2. We are assuming that A comma A, this ordered pair belongs to R2. Then this would imply, that means according to the definition, we have absolute value of A minus A. So here we have to replace the B with A is less than or equals to 5. So absolute value of A minus A, that's simply 0. 0 is less than or equals to 5. Yes, that's a true statement. 0 is less than 5. So it is satisfying the condition, and this simply means that our relation R2 is reflexive. This is a reflexive relation on the set of integers Z. Fine. Now let's go to the second part. So here we will check if it is symmetric or not. For this, we are going to use two arbitrary elements a and b. So let's say a and b are both integers. Fine. Then if we consider the ordered pair a comma b belonging to the relation R2, then according to the definition, this would mean that the absolute value of a minus b must be less than or equals to 5. Okay. Now, the absolute value of a minus b less than 5 can be also expressed as the absolute value of, if we take negative as the common factor, negative of b minus a. This is less than or equals to 5. Now, we know that absolute value does not carry up, so here absolute value of a negative number is still going to be positive only. So we can express it as absolute value of b minus a less than or equals to 5. Now what we're getting here, absolute value of b minus a less than equals to 5. This simply means that we have b comma a belonging to the relation R2. Okay, let's try to understand how we wrote this. So here, how did we define R2? R2 defined as the set of ordered pairs a comma b such that the absolute value of a minus b is less than or equals to 5. Now, in place of the ordered pair a comma b, if we choose b comma a, all we have done is replace a with b and b with a. That in that case, here we get absolute value of b minus a less than or equals to 5. And that's exactly what we're getting. That's exactly what we're getting. So here, if we have the ordered pair a comma b belonging to the relation R2, we were able to show that b comma a also belongs to the same relation R2. So this tells us that our relation R2 is symmetric. This is a symmetric relation. It is a symmetric relation. And okay, and let's come to the final one. We'll check if it is transitive or not. So here we'll be considering three elements a, b, and c. So let's say three elements a, b, and c belongs to the set of integers z, such that we have a comma b, the ordered pair a comma b belonging to the relation R2, and we consider b comma c belonging to the relation R2 as well. Our goal will be to show that a comma c also belongs to R2. Okay, a comma b belongs to R2 simply means the absolute value of a minus b is going to be less than or equals to 5, and b comma c belonging to R2 would mean that the absolute value of b minus c, that's going to be less than or equals to 5. Now, the absolute value of a minus b being less than equals to 5 can be also expressed as we have a minus b lying between negative 5 and positive 5. And absolute value of b minus c less than or equals to 5 can be expressed as negative 5 less than or equals to b minus c, which is less than or equals to positive 5. Now, when we combine these two inequalities that I'm leaving as an exercise for you to try out, is going to be given by a minus c is going to lie between negative 10 and positive 10, meaning that we have absolute value of a minus c less than or equals to 10. But our goal is to show that a comma c belonging to R2. That would mean that we had to show that the absolute value of a minus c is less than or equals to 5. But we are getting that absolute value of a minus is less than or equals to 10. So this implies that the ordered pair a comma c cannot belong to the relation R2. If it does not belongs to R2, provided a comma b and b comma c belongs to R2, would simply imply that our relation R2 is not transitive in nature. This is not a transitive relation. Okay, so here we have shown here that our given relation R2, this is reflexive and it is symmetric, but it is not going to be transitive. Now let's go to the third one, where R3 is defined on the set of real numbers, and it is defined as the ordered pair a comma b belonging to R3 if and only if we have this equation a squared minus 4ab plus 3b squared equals to 0. So let's check for reflexivity. So what we will do, we will consider an element a belonging to the set of real numbers R, such that the ordered pair a comma a belonging to the relation R3 would simply imply, that means if we take this equation, then we can rewrite it as a squared minus 4 times a multiplied to a plus 3a squared equals to 0. So here we have a squared minus 4a squared plus 3a squared. this is going to be equals to 0. So on the left hand side we get 0, and we already have 0 on the right hand side. 0 equals to 0, so this is true. So this is telling us that a comma a indeed belongs to the relation R3 because it is satisfying the equation. So here we say that R is reflexive. R is reflexive. Fine. R is reflexive. Now let's go to the second one to check whether if it is symmetric or not. So here we're going to consider two arbitrary elements a and b belonging to the set of real numbers R such that if we have the ordered pair a comma b belonging to the relation R3, then that simply means that a squared minus 4ab plus 3b squared, this is the definition, this is equals to 0. But to check for symmetry, we have to show that b comma a also belongs to the relation R3. So what does it mean when you say that b comma a belongs to R3? If we look at the equation, we have to change the position of a and b. So wherever we see a, we're going to replace it with b. We get b squared minus 4 times ba, and wherever we see b, we have to replace it with a. So this is the equation that we need to get in order to show that b comma a belongs to R3. But there is no way we can arrange the term of this equation a squared minus 4ab plus 3b squared equals to 0 to get this equation. There is no way. You can try that out. So here let's split 3b squared as into two parts as b squared plus 2b squared, with b squared plus 2b squared. Then we have negative 4ab, but we can also rewrite this as negative 4ba. Then we have positive a squared, but we can express it as 3 times a squared minus 2a squared equals to 0. So now we get b squared minus 4ba plus 3a squared. So this is going to be equals to, so we have 2a squared minus 2b squared. Fine. So here this is not equals to 0. So here we have shown that b squared minus 4ba plus 3a squared, we wanted it to be 0. But here we are not getting it as equals to 0. This simply means that the ordered pair b comma a, it cannot belong to the relation R3. If it cannot belong to R3, then we can immediately say that our given relation R3, this is not going to be symmetric. This is not a symmetric relation on the set of real numbers. Okay, now let's check for transitivity. So here what we'll do, we're going to consider three elements a, b and c. These are all real numbers. Fine. Then what we'll do, we're going to consider two ordered pairs. One of the ordered pair is going to be a comma b. This belongs to the relation R3. And we have another ordered pair b comma c belonging to the relation R3. Our goal will be to show that the relation the ordered pair a comma c also belongs to the relation R3. In other words, so here let's try to understand this. The ordered pair a comma b belonging to R3 simply means that a squared minus 4 times ab plus 3b squared, this is going to be equals to 0. And if we say the ordered pair b comma c belongs to R3, that means that b squared minus 4bc plus 3c squared, this must be equals to 0. This is basically the same equation as a squared minus 4ab plus 3b squared. All we have done is replace a with b and b with c, because we have the ordered pair b comma c belonging to R3. So using the same logic, a comma c belonging to R3 would mean that we have to show that a squared minus 4ac added to 3c squared, this must be equals to 0. Okay, let's try to check whether if it is true or not. Now a squared minus 4ab plus 3b squared equals to 0. We can factorize it to get a minus b multiplied to a minus 3b. This is going to be equals to 0. So here we get a equals to b, or we get a equals to 3b. Now we're going to replace this a value with wherever we see b, we're going to replace it with its corresponding a value. So that means b could be a, or b could be equals to a over 3. So if we use b equals to a, so let's say for b equals to a, so here we get the equation a squared minus 4ac plus 3c squared equals to 0. Yes, we are getting this equation. So this tells us that a comma c belongs to the relation R3. And if we use b equals to a over 3, then in that case we're going to get, so here, what is b squared minus 4bc plus 3c squared? First, let's do one thing. Let's factorize it. So we're going to get b minus c multiplied to b minus 3c. This is going to be equals to 0. So we replace b with a over 3. We'll get a over 3 minus c multiplied to a over 3 minus 3c equals to 0. We're going to multiply throughout with 9. So we are going to get a minus 3c multiplied to a minus 9c equals to 0. Fine. Now, well, when we distribute a minus 3c with a minus 9c, we're going to get a squared minus 12ac added to 27c squared equals to 0. So that means here, since this is not same as this equation, a squared minus 4ac plus 3c squared equals to 0. So here we cannot say that a comma c belongs to R. Here we'll say that a comma c cannot belongs to the relation R3. Now there's a very specific case. Only when b equals to a, then we say that for a comma b belonging to R3 and b comma c belonging to R3, a comma c is going to belong to R3. Whereas if we have b equals to a over 3, in that case, the ordered pair a comma c cannot belong to R3. So that means we're not getting a general case here. We're getting a very specific case. So here we're getting the case that R3, the relation R3 is not transitive, because we need a general case where the relation R3 is going to be true for any values of a, b and c that we choose. So here R3 is not transitive. So for this third problem, R3, this is not transitive. It is symmetric and it is reflexive.